Hi guys, we hope you're doing well and keeping safe. Today, we'll be discussing some examples on line integrals of scalar fields, but for this part of the video, we'll be recalling what was introduced in the lecture so you can proceed to the next part if you'd like to skip the summary. Uh, to start, let f be a function in R squared, that is in terms of the variables x and y, which is continuous over a region containing the smooth curve C, parameterized by the vector function r of t with first and second components x of t and y of t, where t runs over a parameter domain given here by the closed interval ab. The line integral of f along C with respect to the arc length parameter s is defined now by this expression equal to this given limit, provided that this limit exists. So from the definition, to compute for a line integral, we need two things. First, we need a function. Second, we need a curve C, which is parameterized by the vector function r of t over the parameter domain given here by the closed interval ab. In which case, the line integral of f along C with respect to the arc length parameter s is in fact now replaced by this definite integral. So notice that x and y are actually replaced by the components of the vector function r of t given now by x of t and y of t, while the arc length parameter ds is actually replaced here by the norm of r prime of t dt. And then we take the integral from a until b, which is over the parameter domain. So now, what are the applications of the line integrals of scalar fields? So here we have three. First, we could talk about the mass of a thin wire, wherein the thin wire has shape given by c and has density function given now by f. So if in case the density function f is equal now to 1 for all points x, y inside the thin wire, then we have instead the arc length of the thin wire or the arc length of the curve c. For the last application, we could take a look now at the area of a given cylindrical surface. So here, we're looking at cylindrical surface whose base or projection is onto the xy plane and is in fact given by c. So once that the base or the projection on the xy plane is given by c, and the height at each point in c is actually given by the function f, then the line integral is actually equal to the area of the cylindrical surface. Of course, we could take a look here at line integrals in terms of the three-dimensional case, that is in terms of the variables x, y, and z. However, for these three applications, only the first two are applicable. So that is, we could still take a look at the mass of a thin wire and the arc length of a curve C for given space curves. So in which case, if r of t is parameterized now by the vector with first, second, and third components x of t, y of t, and z of t, where t runs from a until b, then the only difference would be our function would now have three variables x, y, and z. And so z here is replaced now by z of t. ds, notice, is still replaced by the norm of r prime of t dt, and the integral is still taken from a until b, or that would be for whatever parameter domain is actually specified. Of course, we could also take a look here at line integrals with respect to the coordinate variables. So that is, instead of having here ds, we could take a look now at dx, dy, and dz. So computationally, dx is replaced here by x prime of t dt, dy is replaced instead by y prime of t dt, and dz is replaced by z prime of t dt. So recall from the lecture that line integrals with respect to coordinate variables often appear together. So that is, if p, q, and r are scalar fields, or scalar functions, then the integral of p over c with respect to x, plus the integral of q over c with respect to y, plus the line integral of r over c with respect to z can be written here as follows. So, what are the differences between line integrals with respect to the arc length s, and with respect to the coordinate variables dx, dy, and dz. So recall from the lecture that first, um, the orientation of the curve C actually matters when we're taking a look here at line integrals with respect to the coordinate variables. So that is, if we replace here c by minus c instead, then we'll introduce here a negative. Um, While if you take a look here at the arc length s, replacing c by negative c in fact does not change the answer. So that is, With respect to the organic parameter s, the parametrization and the orientation of the curve does not matter, while for the coordinate variables, the parametrization does not matter, but the orientation of the curve does matter. So this ends the recall of the previous lecture. So for the next part, we'll be discussing some examples. So if you have questions so far, feel free to go back to the lecture or this part of the video, or you may drop down some comments below.